So welcome everyone to the September 2024 meeting of the Mornington Peninsula Astronomical Society. As usual, we just show a few things that have happened recently, as shown up here on this slide. So the top one on the left shows the asteroid 2024 PT5, which is only 11 metres in diameter, and that's set to become a second moon of the Earth for at least 2 months. As it swings around the Earth and then proceeds to go off on its merry way afterwards. So between 29th September and the 25th of November, we'll, strictly speaking, have 2 moons for that period of time. Next one across, on the top there, if you move one to the right, shows a study that was done by the Keck telescope in Hawaii on the Iris galaxy shown there, and those numbers, which are the RA index of its location. And the Australian National University has been involved with that study. And they were actually quite surprised to see that the size of the galaxies extended a lot further than would be anticipated, even just by the dark matter. And very, very considerably so, such that they conclude that the Milky Way and the Andromeda galaxy are already starting to interact because we're a lot larger than what people have thought in the past. Then over to the top right-hand side, you'll recognise at least the left-hand image there, which is the supergiant black hole in the centre of M87. This was the first one that was released by the Event Horizon telescope, going back now to 2019. And if you remember, they also had one for Sagittarius A star, which is the one inside the Milky Way galaxy. However, I couldn't find an image for that one. This is a before and after image. The one that was released previously is the left-hand side, that was done by the distributed telescopes at 230 gigahertz, and they've now upgraded the telescopes to do it at a higher frequency of 345, which actually improves the resolution. And the resolution now is shown on the right-hand side for the same black hole. I couldn't actually find the equivalent one of Sagittarius A star, but that's the one in the centre of M87.
What's that gas? Is it methane or?
Oh no. This is around the black hole. So this is the gas falling into the black hole, as well as at that distance the photon ring around the Event Horizon. So the Event Horizon telescope is also looking at increasing that even further to improve the resolution even more. Then down on the bottom left there, the Boeing Starliner craft has landed flawlessly back in New Mexico. This was the one that was meant to bring the 2 astronauts back from the International Space Station, who are now stuck up there until February, before they can be brought back by SpaceX instead. And as it turned out, it was flawless. They've identified that the issue that they were having with the thrusters was due to Teflon seals that were expanding, and so were partly blocking the oxidizer in the thruster. So I'm sure they'll now be working on that rather furiously, because it was a bit of embarrassment to take the astronauts up there, but then not to undock and bring them back. Then the one in the bottom middle there is Elon Musk's Starship from SpaceX, doing a rapid unscheduled disassembly back in November. And the Russians kept a very close eye on that, and they've actually published that it caused a very large hole in the ionosphere that lasted for about 40 minutes, and it's the first time that they've seen anything from an artificially made explosion in this case, and it was thought that the propellant may have had something to do with that it caused interaction with oxygen and ozone up at that layer. And over on the right-hand side, we'll show a little bit more about this at a later meeting, is shown one of the 4 astronauts that went up in the SpaceX's Polaris Dawn recently. This was the first private crew to go up for 5 days, and they did all sorts of things up there. So this is privately funded, and they did the first outside spacewalk with them having about 2 hours outside in their nice white-looking spacesuits. And as I say, we'll see a little bit more, and you'll see one of the astronauts here. I think she was the first one actually out the door, holding her violin and playing it in weightlessness. So tonight, welcome to the meeting, and I'll read out as usual the number of new members that we've had since our last meeting. There's Mark Schapper, Daniel Smith, Tina Havel, Fabian Purcell, Clementine Doherty, Heidi Cannon, Michelle Sykes and family, Nancy O'Brien and family, and Lingaswaran Sinathure and family. Any of you here tonight? I think there was one. Welcome to the Society. And I know you've already spoken to our new members, Officer Nerida, across the thing for you. Feel free to come and go as you like during the evening. Don't feel an obligation to sit through listening to the whole event if you need to leave early. If you have any questions of the Society, feel free to either ask Nerida, or if she's not here, any of the others on committee as well. We'll quite happily try and make you at home, so welcome. I'll also look at the events of the past month and the coming month, and then Chris will do the monthly photo challenge. You notice he's not in the room tonight, but he will be joining us by Zoom. And by the time delay in the connection, you can sort of work out where he's located at the moment as well. So there's about a 2-second delay, so it's probably round about the moon to go there and back in that length of time. Yep, he's nodding. Then we'll go across to Sky for the Month from Guido, and then we'll look at our Mathematical Universe by Max Tegmark. This is one that Eden posted a week or two ago as part of a book review that he did online. Then we'll close by looking at the future of the history and the future of the solar system from the earliest times before the solar system came into existence. So the planets actually existed before the sun turned on, and going forward in time to the end of the universe, what it will actually look like going forward. The recent events, we had quite a busy September, as you can see there by all the writing on the screen. We started off with, since the last meeting, with the Working Bee and the Members Barbecue. Then we had Strathcona Grammar out at Merrick's camp, and we had 27 of them, and unfortunately it was quite cloudy, but nevertheless they got to see some things while we were out there. Then we had the committee meeting, and there was a fair amount discussed at the committee meeting. We've got the new all-sky camera, which will come in probably in the next month or so, I suspect, or maybe it's already it's already functioning. We've got a new gate next door which leads to the toilets in the Echo Centre, thanks to Phil's efforts, and he's been busily getting the pathway ready as well, so you'll be able to go out there and across to those toilets in the future, rather than necessarily using ours if they're occupied. Then a couple of days later we had Yarra Valley Grammar up here. They were staying at the camp next door, and we had 61 of those, and pretty good viewing conditions actually, not much cloud in that night. Public night was a couple of days later, and Trevor had 56 members of the public, but alas nothing was seen because it was completely clouded over. On the following Monday we had Our Lady Help of Christians Primary School to the Briars. They were also staying on camp next door, and they had no cloud at all, and they had to sit through Catherine and myself speaking with them, but lots and lots of questions, which is really good to see. Then the week really hotted up. The very next day we had Toorak College. The first group was bussed in here, or coached in here, and we had 43 of them and virtually no clouds, so they all got a good viewing outside. The very next day we had the scouts drawn from right across the district, from Carrum Downs to Langwarrin to Ballon Park, Baden Powell, Frankston and Seaford all came, so they were all coordinated as one entire district. So we had 70 of them asking lots and lots of questions, very fascinated by black holes. They had quite a bit of cloud, but nevertheless they got to see at least Saturn and the moon. Then the very next day we had Toorak College again. A little bit cloudier, about 80% cloud, but nevertheless they did get to see something before they left, which was really good, especially with Saturn. And on Saturday, I wasn't actually at the astrophotography workshop. That's the one of the photos taken in the background there by Greg. And that shows Chris and member Sylvia Kozlov, I think it is, somewhere around there. Yep, Kozlov, and Nerida as well, winning the Optics Central Prize from that workshop. And they had a really good turnout. You obviously, for these sort of events, get a few fall away at the last moment due to sickness or similar sort of things. And they had a bit of cloud there, but certainly a lot better than what it could have been, you know, given that the conditions have been pretty unsettled lately. And lots of talks there shown by the members actually named at the bottom. Coming up soon, we're getting a bit of a breather this month. So we got the Cosmology Discovery Group this Saturday at 1:45 here, and the working bee afterwards at 4 p.m, followed by the members' barbecue. Then the public stargazing night that's already been booked out for quite some time now will be on the first Friday of the month, 4th of October. The next monthly meeting then is not on the 16th of October, so we don't have any scouts or schools in the intervening period. And of course, with the school holidays, that helps keep those number of events down as well. And the next big event coming up, which is after the next monthly meeting here, is the Telescope Learning Day. And the bookings have probably increased a bit since I updated this slide a day or two ago. Although we've capped it at 85 attendees, I think that number is probably going to be a little bit bigger because some members just turn up rather than actually book, and we wish they would book for catering purposes. And the last thing to mention that Jamie's already posted out on Facebook and on eScorpius is about the Astronomy 2025 Almanac, which sadly will be the last one that Quasar will be publishing. Ken Wallace, Glenn Dawes and Peter Northfield, I think, are looking for a bit of retirement. They've been doing it for 35 years, and it's very much a labour of love and very much a lot of work to do each year. If you wish to pre-order one, it's for members, it's $25 at that link shown at the bottom there, which you can go to now so that we know how many to order.
We are go. All right. Doing Astromofo from Moonbase Alpha this week because I'm on remote assignment. But okay, so the last Astromofo was Indigenous astronomy, objects which are related to Indigenous constellations and Indigenous themes. We had a few members who managed to get photos and images, and this one here is by Steve Wilkins, which is in Corona Australis, which is also Wan, the boomerang in Indigenous cultures. And this is with his ZWA 1600mm camera, monochrome camera with RGB filters. And it's got the globular cluster there as well, and the reflection nebula and the dark nebula going through. And I'll show you later on just whereabouts in Corona Australis is. So I would also just like to say we acknowledge the land, water and sky under which we meet today are of the Bunurong and Bunurong peoples, and we pay our respects to their elders past and present. And this challenge was completed by Steve Wilkins, Lee Hornsby, Jamie Pole, Sylvie Grandit, Jamie Pole twice, no, only once, and Liam Lowe. And what we have here is part of Jewett, the red-rumped parrot. So many of you will recognise this as Xantares and the Roophiuchi complex in Ophiuchus and Scorpio. But to the indigenous cultures, it's the rump of the red-rumped parrot. And Antares, the bright yellow star, signifies the back end of that constellation. And I'll just show you a little later on how that all fits in with Scorpio. So this was taken by me with my ASI camera with just a standard 70mm lens attached to it, and with a filter drawer and some filters. And this is Corona Australis. So we can see the boomerang here, taking that shape there. And the reflection nebula and the dark nebula that was in Steve's photo is just in that section of Corona Australis there. And again, this was by me with my ASI camera and the same 70mm lens as the previous one. Aurora Australis is also of indigenous significance because they see it as campfires of spirit people. Sometimes it's a bad omen, sometimes not a bad omen. It's also thought that some elders were able to communicate with spirits through the aurora, or to read the aurora as messages from the spirits. Oh, and that one there was by Lee Hornsby on 12th of August. There was a bit of an aurora happening. So we've had a couple of auroras past couple of months. This one was by Jamie Pole. There's a bit of a time lapse here. And apart from the aurora, you can also see the large and small Magellanic clouds, which are the male and female brolgas in indigenous astronomy. They see them as male and female brolgas. So this wasn't an overly powerful, hang on, it was reasonable, but yeah, nice time lapse there. Okay. This is another one from another aurora in July, taken by myself also in Tooradin. And again, the aurora, we've got the brolgas over there, and yeah, nice little time lapse. Ah, and the emu. There we go. There's another one. You know the great emu in the sky. And that was on the 24th of July. Sylvie Grandin got a couple of nice photos of the moon and the sun with the new sea star just the other day. So the moon, different cultures call them different things. This is what's called Ngalindi, I think it's pronounced. I'm not exactly an expert, but oh, hang on a second, I've got something to read about that. It was, okay, so the moon, Galindi, is generally male in indigenous astronomy. It's a male symbol, and he was a fat, lazy man, which corresponds to the full moon, for which his wives punished him by chopping off bits of him with their axes, producing a waning moon. So as the moon wanes, that's Galindi being slowly chopped up by his wives for being a fat, lazy old man. He managed to escape by climbing a tall tree to follow the sun, but was mortally wounded and died. That's when we get the new moon. After remaining dead for 3 days, he rose again and gradually began to grow round and fat, and that represents the waxing moon, until 2 weeks later, all this starts again, and his wives are attacking him again and kill him again. Then the cycle just keeps on repeating. The sun, Jindu, is a woman. So generally we said that the moon is a male character. The sun is a female character in a lot of indigenous astronomy. And Jindu is a woman. The sun is the source of life and death, bringing life and heat to the people. And that's from Sylvie Grandin. Liam Laub captured this one on the 19th of August from McRae, which I'd shown previously. And that's just the moon rising with the trees there in the foreground. And this one is Carrick Carrick, the Australian kestrel. We see it in the tail of Scorpio over here, but we can see the stars over there in Scorpio's tail just making the symbol of an Australian kestrel. And over here we see the red-rumped parrot, which is the other end of Scorpio, and with Antares just there in the tail of the red-rumped parrot. Okay, sources for the, indigenous astronomy information. Aboriginalastronomy.com.au is a terrific source which has got a lot of information about different Aboriginal symbols, what they are to different cultures and how they're interpreted. Also, I've mentioned previously the Stellarium star law, in Stellarium. If you go to the options of configuration, and you can activate different star laws, and there's a couple of indigenous ones there. And we also have a collection of articles by Ian Sullivan, which is available on request as well. Okay, our next challenge. Now, Peter was mentioning about galaxies and the Milky Way being deformed by our interaction with Andromeda at the start. So galaxies is our next topic. We've done galaxies before, but I thought we'd give it another go. So we've got our own galaxy, obviously, the LMC and SMC. Andromeda is also up in the sky at the moment, but you do need to be quite, a fair bit further north of Melbourne so that you don't get it interfering with the light pollution. And then there's quite a few galaxies that we can image in Sculptor, Grus, and Parvo as well with telescopes. So submit the photos to MPAS members' Facebook page or the eScorpius, or to eScorpius, or email them to myself. And the photos just need to be taken during the time of the MOFO challenge, or added to during that period at least anyway. And that's me.
So that brings us to Sky for the month for September and October. And starting with the inner solar system, we can see, well, the sun in the middle and Earth over here. We can see Mercury is basically between us and the sun at this point, so we won't be able to see it very much. And Venus over here and Mars are actually visible in the sky. If we fast forward a bit from, well, this is end of August, and now through September. We see that we are catching up with Mars, and Venus is a little bit behind us. We'll see in the all-sky image a little bit later what that looks like in the sky. Well, I was supposed to zoom out as well to the outer planets. Let me just go back and try that again. So zooming out, one thing we can see is that Saturn is at opposition at the moment, right? So it means that we are exactly in between Saturn and the Sun, which means that it's at a perfect time for us to view. Neptune is also very close to opposition, right? So because we're traveling a bit faster, we're catching up with Neptune, and we'll basically be in a direct line between the Sun and Neptune very soon. And we're also catching up with Jupiter, which means that Jupiter will become a bit more visible in our night sky. At the moment, it's still a morning object, pretty much. All right, so let's look at the night sky on the 1st of October. So you can see Venus here far enough from the sun that we can actually see it after sunset. But Mercury is very close to the sun, so there's nothing to see at the moment. Sunset around 6:30. The equinox obviously coming up on the 22nd of the month. And daylight saving starts on the 6th of October, so that's coming up in the next month as well. Venus is a very bright evening object at the moment. I'm sure you've noticed it in the sky. And then the other planets that are visible during the evening. So this is around, I think, 8:15 in the evening on the 1st of October. We will have Neptune basically visible all night, right from sunset through the entire night. It's just past opposition, but at a very good time to view it now. One thing to look out for with Saturn at the moment is that you can see, well, first of all, the rings are almost closed. So I just had a look at the APW through Big Blue here, and it was really interesting to see that the rings are basically edge on, so you can't really see through them anymore. It's just like a bit of light across the body of the planet, so you can't really see them as rings anymore at the moment. But we should be able to see Saturn's shadow on the rings as soon as we're a little bit past opposition. Because at opposition, the shadow is directly behind the planet, so we won't be able to see it. But now that we that we're a bit past opposition, we should be able to see the shadow of the planet appear on the rings again. So that might be an interesting thing to see. Neptune will be at opposition on the 21st of this month. Okay, continuing a bit through the night, you can see that the Milky Way now is a lot further in the west and a lot lower on the horizon than just last month or a couple of months ago. You can also see that the Southern Cross, the pointers, are quite low in the south now, right? So we're running out of time for those kinds of objects, for things like the Jewel Box, the Southern Cross itself, Omega Centauri, and so on, right? So it's pretty much the last chance to really observe them well for a couple of months or so. But then we've got another few objects coming up. So just looking at the constellations, we still have all the winter constellations, so Scorpius is still in the sky, but we will see Orion now rise again a bit earlier. I mean, this is 10 o'clock where it's still below the horizon, but yeah, that's definitely changing in the next couple of months. So continuing a bit further through the night, we have the other planets coming up there. So we have Uranus and Jupiter rise around midnight or so. Yeah, Uranus around 11 p.m., Jupiter just after midnight or so. Jupiter will go into retrograde motion from the 9th of October. Mars now rising around 2 a.m., so definitely a lot earlier than just a couple of months ago. And it will be at its western quadrature on the 14th of October, which means that it's in a 90-degree angle between the Sun and Earth. And that means that Mars will actually show as a crescent, not a big crescent, but you will show that it's not just a round disk, but I think that's something interesting. I haven't actually seen that through a telescope yet. And so yeah, around mid-October would be a good time to see that. I think Mars will be in opposition early next year, so that's still a little bit of time. But this time, it'll be almost at its furthest point from the Sun in its orbit. So it'll be pretty small at opposition this time. So it's also still quite small at the moment. All right, so this is 5 a.m., so we're getting closer to sunrise, I guess. So Mercury will be at superior conjunction on the 1st of October, so will disappear from view for us. And the moon, well, we have an almost full moon. What's the date today? Is it the 18th already? So yeah, and then we have the next new moon on the 3rd of October, and a full moon on the 17th of October, and that's going to be what the media always calls a supermoon, which just means it is at its closest point in its orbit, which makes it a little bit bigger. Not really something you can see with the naked eye, I guess, but yeah, so we will have a supermoon on the 17th of October. Sunrise is around 6 a.m. now, so again, a lot earlier than just a couple of months ago. Right, here is just a comparison of the apparent sizes of the planets at the moment, and you can see Mars is definitely getting bigger because we're catching up to it in the orbit. And yeah, I think this, you can see that Saturn's rings are pretty much closed, but I think through a telescope it looks even more strange than just in the image here. All right, just a couple of topics to revisit from previous Sky for the Month. So I'm not sure if it was last month or maybe a couple of months ago, but I talked about the possible nova in the constellation of Corona Borealis. So the star T Corona Borealis is expected to to go nova, so to shed some part of its outer hull, and then it should brighten to 3rd or 2nd magnitude, so very easily visible naked eye. But if you look at where Corona Borealis is at the moment, down here, it's already very close to the horizon. And so this is today, so if we just fast forward a little bit, you can see just in a few days, it'll basically be below the horizon and very close to the Sun. So not a chance to see anything, if anything happens in the next few days. So If we're really unlucky, we will just miss it. And it'll happen exactly when it's so close to the sun from our point of view that we can't see it. But maybe there's an opportunity when it comes back the other side. So we will have to see. The other thing is the comet that's currently in the sky, Tsuchinshan Atlas. So it's passing through Leo, Virgo, Serpens, and Ophiuchus, rising just before dawn. It's currently magnitude 3 or something in that region. And it's going towards its perihelion on the 27th of September, which means that's the closest point to the sun in its orbit. Obviously the most dangerous point in its orbit as well, because it heats up. It might just break apart at that point. We don't know. But at the moment, it's still observable. I think I have an animation. So it is fairly close to the horizon. I think this was yesterday. But if we fast forward a little bit, you can see that it's getting a bit higher in the sky around like 5:30 in the morning. But then also the sun rises a bit earlier every day now, right? So we're basically in a race against that. So there might be an opportunity over the next few days or next couple of weeks to see it. And then again, on the other side, this is when it's basically come around, and now it's an evening object around 8:30 p.m. You can see it will rise a bit higher in the sky from about mid-October, but then again the sun will set a bit later, so we're also struggling a bit with the sunlight then. All right, finally, meteor showers. We have the southern Taurids from the 20th of September to the 20th of November, peaking a bit later in November. And those should be best to view after the moon sets around the peak, which is around 1 a.m. or so. And then the Orionids from the 2nd of October till the 7th of November, where this year, unfortunately, the viewing will be affected by the moon around the peak of the Orionids, but might still be like a week before, a week after, might still be possible to see something. All right, and my sources, as always, were Stellarium, the NASA Eyes on the Solar System website, and the Astronomy 2024 yearbook. Right.
We'll go into the main talk. So this talk goes for about 45 minutes, but then there's about another 45 minutes of questions after that. So that'll probably keep us going until around about the 10 o'clock mark. If you need to get up at any stage to go to the bathroom or have a cup of coffee, feel free to do so. Just quietly move out the back. This is Professor Max Tegmark. You may actually recognise his face. He's been around for quite a while, very famous cosmologist. And he also works in the AI space as well. So Time magazine named him last year as one of the top 100 most influential people in the world in AI. He's Swedish born and is at the Massachusetts Institute of Technology in the USA. Now this public lecture is now getting on for 10 years old, but nevertheless the subject matter is still the same. And he's put forward in his book by the same name, Our Mathematical Universe, an idea of how maybe the universe is actually not just based on maths, but is a result of maths. So let's have a look.
So I want to encourage you to think big, because we humans have again and again and again underestimated not only the size of our cosmos, discovering that everything that we thought existed was just a small part of a much grander structure, a planet, a solar system, a galaxy, a universe, and maybe even a hierarchy of parallel universes. But we've also repeatedly underestimated the power of our human minds to understand and even improve our cosmos. Now, to understand what I mean about the first part, underestimating the size of things, we have to remind ourselves of what we humans have managed to figure out so far about our place in space. So let's do that by going for a little ride together here. Let's start in the Himalayas and head up a little bit. When ancient cave dwellers looked up at those sparkly white dots in the sky. They had beautiful myths, of course, for what this was all supposed to be, but I think many of them at the same time felt a little bit melancholy, figuring that they would never be able to know for sure, what the stars really were. But they were wrong. They really underestimated the power of our human minds, because we've subsequently realized that we could figure out the stars. We didn't even need rocket power, but just mental power, letting our minds fly. With pure mental power, Eratosthenes, over 2,000 years ago, cleverly figured out the size of the Earth to be 40,000 kilometers in diameter. And since then, the same kind of ingenuity has actually given us rocket power. We see here exactly the scale where all the satellites are orbiting our planet right now. The near-Earth comm satellites in green, and then geostationary satellites and others farther out. This is fully to-scale rendering made by the American Museum of Natural History in New York. And as we zoom out farther, and the moon's orbit starts coming into view, where is the moon? You can't even see it, because this is actually exactly the scale. This is not like in one of these kids' books where things are expanded. And this gives us a sense of how vast things are. Our sun, you see here, we all know it takes about 8 minutes for the light to reach us from it, just to get a sense of scale. And as the planets come into view here, we're seeing things which are so big that it takes hours for light to reach us from the outer solar system. Now, I would like you to raise your hands if you know anybody who was born before 1925. I know. So I see a lot of hands. These people that you're now thinking about, they, in a sense, were born in a much smaller universe than us. They didn't know back then that there were other galaxies. What's coming into focus here, the Milky Way, with its hundreds of billions of stars and its majestic spiral structure stretching 100,000 light years from side to side, it only became clear that there are other galaxies in 1925 when Edwin Hubble discovered that. And yet this much grander structure that we're all part of, we now know, of course, is also just one out of billions and billions of other galaxies, which together form even larger structures, groups, clusters, superclusters, and enormous filaments. And we see here the Sloan Great Wall that I and my colleagues discovered in this enormous 3D galaxy map, which is a billion light years from side to side. And that, too, is in turn just part of an even grander structure, what we affectionately call our universe. When astronomers talk about our universe, we don't mean everything that exists, or even all of space. We just mean the spherical part of space from which light has had time to reach us so far during the 13.8 billion years since our Big Bang, because stuff outside of that, if it exists, if there are more distant galaxies here, no telescope could see them. We would have to wait billions of years more for the light to have time to get here. Now, so far, most of what I said is pretty intuitive. The farther away we look, of course, the more stuff we see. But what on earth is this round ball and with all these funky yellow and green and blue colors? To appreciate and understand that, it's not enough to talk about our place in space. We also have to explore our place in time. Fortunately, that's remarkably easy in astronomy, because looking into the sky is like looking into a time machine. We already talked about how we see the sun, not the way it is now, but the way it was 8 minutes ago. If you see some stars this evening, if the rain clears up, you'll see them maybe hundreds of years ago. So somebody out there looking at us, they wouldn't see us, but they might see the American Revolution or something, or Shakespeare doing his things. And if we look really far out with a good telescope, here we see many galaxies the way they were billions and billions of years into the past. So by simply looking at different distances from Earth, we can actually watch how cosmic history has unfolded. Now, what have we learned from this? Well, we've learned something very, very surprising. And to fully appreciate how surprising these things are, I'd like you for a moment to just imagine that each one of you is a galaxy. And I'm looking at you with my telescope here. What do I see? First, I see something really funny, which is all of you guys here in the front seem like you're about 90 years old. And then I see a bunch of people here, maybe 70, 60, and 50, and I see way up there a row with just teenagers. And then I see a bunch of toddlers. And the second last row is only infants. And the very last row is entirely empty. And as if that weren't surprising enough, the whole back wall of this lecture theater is glowing at me with a strange glow of microwaves. And it's more puzzling still, because for some reason you're all blushing. You guys here just a little bit pink, but those of you in the back look possibly tomato red. This is exactly what we see when we look at these galaxies out there with telescopes. So what on earth does this mean? Well, first of all, why did you seem to order yourself by age as you walked into the lecture theater? Well, we've already talked about how the farther away we look, right, the longer ago we're seeing things happen. So that means that the galaxies that I see near me here are galaxies which are quite old, almost 13, which have been around long enough to mature and grow up and become big and look much like ours. Whereas if I look really far away, I'm looking so far back in the past that galaxies hadn't had time to grow up and mature. We see juvenile and really far away, just these tiny baby galaxies. And if I look really far away, corresponding to the last row of the lecture theater, I see no galaxies at all, because I'm looking at what happened so long ago that galaxies had not yet had time to form. Why were you all blushing? Are you embarrassed to be here tonight with me? Well, we know that if you go down to the highway and you listen to cars, you hear them go, ew, ew. They do not sound, ew, ew. This is because what we know is the Doppler effect, where, as you know, something going away from you has its frequency lowered. And the exact same thing happens with light. So if a galaxy is flying away, the light frequency will be lower, which means its color will look redder. We call that redshift in astronomy. So the fact that you're all blushing means that all of you guys, for some reason, are flying away from me, which is what we mean when we say that our universe is expanding. I can figure out how long ago you, for example, were right here by just taking your distance and dividing it by your speed. And remarkably, when Edwin Hubble did this for the first time, he found that the answer he got was pretty much the same for every galaxy, because galaxies that were twice as far away were flying away twice as fast. That's why those of you in the back looked more tomato red, and those nearby were just blushing a little bit. So, and when you do the math, you find out that about 13.8 billion years ago, pretty much all the galaxies we see were more or less in the same place. So there was some grand calamity that took place back then. We don't know exactly what caused it or exactly what happened, but we have a fancy name for it. We call it our Big Bang. We can come back and you can ask me much more about it later if you'd like. But we have a very good idea of what happened during the 13.8 billion years since, because we can see most of this with our telescopes. So what's the last strange thing I mentioned, the fact that the rear wall is glowing? How can we understand that? Well, all this black stuff in space pictures, which I used to think was vacuum when I was a kid, can't be empty space because the galaxies must have formed from something, right? And we now know that this is mostly hydrogen gas, which gravity later clumped together into galaxies. Now, if everything's expanding, then so is a gas. And you know, if you expand a gas, it cools off. That's how your refrigerators and air conditioners work. So as we go farther and farther into the past, this gas must be hotter and hotter and hotter. And if we take an ice cube and we heat it up, it turns into liquid water. If we heat up the water, it turns into, let's have one of the kids answer. What does it turn into here? If I heat up water enough, yeah? Steam, very good. Now, what if I take a gas, like steam, and I heat it up more? What does it turn into? Grown-ups can answer too for this one. Plasma, exactly, which means that the electrons get torn off from the atoms. Now, a plasma is opaque, not transparent like this gas, so it looks to us like beyond all those galaxies and beyond the empty last row where there were no galaxies, we see a plasma screen glowing at us. But it's going to look, of course, exactly the same whatever direction we look, if we look that far into the past. So it actually looks to us like we are surrounded by this plasma screen that we can photograph from inside. And here are some of these remarkable photos of this plasma screen made by the Wilkinson microwave anisotropy probe, a satellite I had a lot of fun working with data from. One of the most successful NASA missions ever. It revolutionized cosmology for a cost of about 25 pence per American. And I just thought I'd mention that since so many of my American colleagues seem to think that they're spending these enormous sums of money on science when they're actually not. Now, you have to ask yourself, though, when you take pictures of what happened 13.8 billion years ago when our universe was only 400,000 years old, how do we know that they're correct? This is a really hard measurement. Well, you do another satellite, which is even better, and you compare. And the European-led Planck satellite, which just released its data last year, gave us this even sharper image. And it's just astonishing how well it agrees. Look at any one spot here, and it's still there, except now it's not 3 megapixels, but 50 megapixels. Fantastic, fantastic data. So in summary, we humans have kept discovering more and more things about our cosmos and have a pretty good understanding of the last 13.8 billion years. But it's important to not get hubris. We have to be modest also of how much we still do not understand. For example, we've come to realize that we have no clue what 95% of our universe is made out of, and that the part we don't understand is at least 2 separate mysteries, dark matter and dark energy. You can ask me more about that afterwards. We would really like to know, in particular, what the dark energy is, because it's going to determine the ultimate fate of our cosmos, whether it's going to keep expanding forever or come crashing back on itself in a big crunch or something else. We also would like to know more about what really happened early on in this Big Bang, what caused it, etc. There are many things we would like to understand better. So how can we do that? Fortunately, we have only harvested a tiny fraction of all this data yet. It's this data which has transformed the field so much. From when I was a grad student and we argued about whether our universe was 10 billion years old or 20 billion years old, until now, when we argue about whether it's 13.7 billion or 13.8 billion. So let me show you how much data we have left to try to collect. If you look inside of this, on the same scale, these beautiful baby pictures of the cosmic micro background, the plasma screen, cover less than 1% of the volume, just a yellow little surface here. And all those galaxies you flew around in earlier are just this dinky little stuff in the middle here. Again, less than 1% of the volume. So most of this is uncharted territory. How can we map that? We can't look here with an ordinary telescope and look at the galaxies because there are no galaxies so far away. They haven't formed yet. Fortunately, there's a very, very cool technique which can do precisely this, which can actually image simply the gas itself and see what it's up to and where there are clumps of it, etc. Because hydrogen gas turns out to give off radio waves. They're 21 centimeters long when they're emitted, and by the time they get here, the expansion of the universe has stretched them to longer wavelengths. So by looking at how long they are when they get here, we can figure out where they came from and make amazing 3D maps here in principle. It's very hard. No one has succeeded yet. A bunch of teams across the planet are competing to try to do this. We are part of this competition at MIT, and I want to show you in just 2 minutes how to build your own radio telescope. That was easy, huh? Thank you. It's one of the most fun things with being a scientist is to get to work with so many awesome students and other researchers who are just so inspiring. And another thing you notice about this is there were no moving parts at all in this telescope. It doesn't look at all, in fact, like one of those big radio dishes that you saw. Have you seen, raise your hand if you saw GoldenEye, the Bond movie, for example, where the Arecibo telescope was in. It's because we've discovered that using a technique that George Ryle here in Britain invented, you can, instead of building expensive dishes, just buy a lot of mass-producible small antennas and cover a large field with them, and just measure the volts in all of them, and then feed all those volts after careful amplification into some really massive computing equipment and have the computers just figure out what the sky looks like. And since computers are so much cheaper now, that turns out to totally be the way to go, building really large radio telescopes like this. We can image not just a small part of the sky at a time, like traditional astronomy, by pointing your telescope, but we can figure out what the whole sky looks like, boom, all at once. And here is a bunch of the friendly students who I worked with to build this, and we're now joining forces with some more colleagues to build one of these, hopefully that covers about 1/10 of a square kilometer, which should help tackle further many of these open mysteries that I mentioned earlier about dark matter, dark energy, our origins, and our ultimate fate. Now, I told you in the beginning that I feel we humans have been the masters of underestimation, and how we've again and again realized that everything we thought existed was part of something bigger, but how at the same time we had underestimated ourselves and our ability to understand things. And it really is quite remarkable to think that those same cave people, maybe who didn't think they could ever really know what the stars were, we're no smarter than they are, but we've now managed to figure out in quite some detail what happened during the last 13.8 billion years. So why is that? How have we humans been able to figure out so much? Partly, of course, it's because the human mind turned out to be even more amazing and versatile than they thought. After all, they hadn't even imagined that you could do such a thing as writing and so on, let alone invent telescopes or program computers. But I think there's more to it as well. We've discovered two extremely powerful ideas in science, and both of them were, in a sense, first really established firmly here in London, and partly here in this building. The first one was, do experiments. And the second was, once you've done experiments, use mathematical modeling to try to describe the data that you see. And we've almost gotten so used to this in science that we forget to ask why this works. But I want to ask why this works. I explore this a lot in the book. And I think the reason it works is because nature turns out to encode all these hidden mathematical patterns and shapes and regularities. So this approach of experiments and mathematical modeling helps our minds find these clues, these mathematical clues, which we can then use to predict the future better, to develop new technologies, and so on. And this is a very old idea, of course. Pythagoras, over 2,000 years ago, said that numbers seem to rule the universe in some sense. And about 400 years ago, Galileo said that our universe is a book written in the language of mathematics. But where is all this math that these guys are talking about? I mean, I look around in the room, I can't even see any numbers anywhere. And when we look at Galileo's quote here, though, we see that although many people think of math mostly as a bag of tricks for manipulating numbers, or maybe, like my mom, think that it's a sadistic form of torture invented by school teachers to make us feel bad about ourselves. Galileo thinks of math in a broader sense. He talks here about shapes and patterns, and of course, geometry is a key part of mathematics, and modern math books often don't even have any numbers in them at all now. It's much more abstract than that. And shapes and patterns is certainly something we have a lot of in nature. Right? If we throw an object and it moves under Earth's gravity, it always moves in the same shape. What do we call this shape? A parabola, exactly. And it's described by a very simple equation, like y equals x squared. whenever we look in the sky at things moving under gravity, again, they all move in a simple shape, regardless of whether they're orbiting a star or a black hole or something else. So what do we call this shape? An ellipse, exactly. It obeys, again, a very simple equation. And moreover, these two shapes are related because if you look at a very tiny part of an ellipse, it's very well approximated by a parabola. And if you do this traditional school math problem of figuring out how an object moves here, more carefully, you see it's actually not the parabola. It's actually exactly a piece of an ellipse, which Isaac Newton first showed. And I have a very bad habit, because I'm a physics professor, which is I love giving unannounced pop quizzes. So you're going to get one too now. But don't worry, it won't contribute to your final grade. It's just diagnostic. So here are three discoveries. The discovery of Neptune, discovery of the radio wave, discovery of the Higgs boson. What tool was it that triggered the discovery of these three things? Any takers? This is a group quiz. Yes, I'll just shout out. Maths. Exactly, it was maths. Or if you want to be really finicky, you could argue that it was technically the pencil, because they were all predicted from mathematical calculations. Adams here in Britain and Urbain Le Verrier in France realized that the planet Uranus was just not moving according to Newton's equations quite exactly as it was supposed to. So they calculated and calculated and calculated, and one of them wrote a letter to this astronomer Gall in Berlin and said, hey, point your telescope at such and such a direction in the sky at such and such a time and you'll find a new planet. I don't know what Gall thought when he got this letter. Maybe he thought that this letter writer must be cuckoo for Cocoa Puffs. But he was certainly curious enough to try, and boom, there was Neptune, predicted through mathematics. And just a few decades later, here in Britain, James Clerk Maxwell was studying realized that he could unify all of electricity and magnetism in the Maxwell equations, and he did more calculations and predicted that if you built a certain kind of device, then you could use it to send information at the speed of light through empty space, through walls, etc. The device was, of course, built, and you all know the results. Raise your hand if you have a cell phone in your pocket. Yeah, predicted through mathematics again. And most recently, of course, Peter Higgs took the most advanced mathematical description we had at the time of nature, the so-called standard model of particle physics, and calculated and predicted that if we humans built the most advanced scientific instrument ever built in Geneva and used it to crash particles together near the speed of light in a certain way, we would there discover a new particle. You know the rest. We built it. Boom. There was the Higgs boson, and he got a free trip to my hometown of Stockholm as a result. And it's not, the power of mathematics isn't limited, of course, to just these three examples. There is an incredible wealth of predictive power in math, much of which is summarized in equations of physics, like these here. And some people have been so impressed by these equations that they even put them on their tombstone, like Schrödinger. And it's not just equations either, it's even numbers, just pure numbers. In my book, you'll find this table here with 32 numbers, pure numbers with no units on them, which remarkably can be used together with those equations to calculate every single fundamental physical constant ever measured in the history of science. You can make more than 100,000 different measurements of various numbers to do with what colors of light come out of atoms, for instance. You can calculate them all from these 32. If you want to know why is it that the proton is 1,836 times heavier than the electron, you can calculate it from these numbers. And so with any other constant you want. So why? Everything I've said so far is pretty uncontroversial. But this is where it gets controversial. What do we make of this? By 1960, Eugene Wigner was so puzzled by this, he wrote this famous essay where he argued that this enormous usefulness of mathematics in the natural sciences is really something bordering on the mysterious. And he said there's no rational explanation for it. In the book, I explore the whole spectrum of possible answers to this, from a lot of people who say it means nothing, to people who say, well, it's very useful, that's what it means, but that's all really we can say about it, to people who think maybe somehow it's all about something with our brains, maybe we invent math. But I also explore the opposite extreme, that it really means that nature is deeply mathematical. at root. In particular, I explore the hypothesis that our universe isn't just described by mathematics, but that it is mathematics in the sense of being a mathematical structure, which I explain carefully in the book what I mean by. So, crudely speaking, this hypothesis is that our world doesn't have merely some mathematical properties, but that it has only mathematical properties. We know that we can often take a complicated mathematical structure and describe it by approximately with some simpler math, just like we could approximate Einstein's really awesome theory of gravity with Newton's simpler theory of gravity pretty good. So if this picture is correct, then what we physicists have unwittingly been doing all along is finding better and better math approximations for the correct equations that we haven't found yet. But hopefully one of the younger talents here in the audience can find, the correct theory of quantum gravity that everything else we've done is just trying to approximate. Now, this sounds pretty crazy, saying that nature has only mathematical properties, because that's absolutely not how it seems, right? So to address this a bit more head-on, I want to introduce you to Mr. Hoggles. Mr. Hoggles is a groundhog, or a woodchuck, as some people prefer to call him. And he lives in our backyard. Actually, he would probably claim that we live in his backyard and that he moved in first. If you ask what are his properties, they don't seem like very mathematical properties to me. Maybe the property of cuteness, the property of passion for grass eating, or obsession with digging holes in our lawn, or herbivorousness. Yet, as physicists, we know that Mr. Hoggles and everything else in our universe is ultimately made up of elementary particles, like electrons and quarks. And what properties does an electron actually have? An electron doesn't have the property of cuteness. It doesn't even have a color or a smell or a texture. The only properties that the electron has, as far as we can tell, and as you can see in this table here, are properties like -1, 1/2, and 1. Right? Now, we physicists have come up with geeky names for these properties, like electric charge and spin and lepton number, but the electron doesn't care what we call these properties, because they are just fundamental mathematical properties. They're numbers. And to the best of our knowledge, and the same goes for every other elementary particle that makes up everything in our universe. That they are purely mathematical objects in the sense that they have no properties at all, except for mathematical properties. Now, if all the stuff in space is purely mathematical in that sense, what about space itself? What properties does space have? It has a property 3. That's the largest number of fingers they can hold perpendicularly to one another, right? We have a nice nerdy name for that too in science, right? We call it the what? Don't be shy. What is 3? Yes, the dimensionality of space. But again, space doesn't care what we call it. The property, that's just human language we invent. What we did not invent is the fact that it's 3, the property itself. Einstein discovered that space also has some more properties called curvature and topology, which are also purely mathematical properties that mathematicians study. So, and to the best of our knowledge, then space itself also is a purely mathematical structure in the sense that it has no non-mathematical properties that we've been able to find. So if we take seriously this idea that both space itself and everything in space has no properties except mathematical properties, it starts to sound a little bit less insane, the idea that maybe everything is, in fact, purely mathematical. Now, so to come back to the main theme here, I've said both that we humans have kept underestimating the size of our physical world, and also that we've kept underestimating our power to understand it. And I've argued that the reason we have been so successful in understanding the world much better than we ever anticipated is because of all these mathematical patterns that were hidden in nature that our cave-dwelling ancestors hadn't noticed yet. So what does this all mean? Well, if this hypothesis that it's all mathematical is wrong, then it means that physics is ultimately going to be doomed. We're one day going to hit a roadblock beyond which we can't proceed, because we've discovered all the mathematical patterns there were to discover, and the rest of the stuff that we still don't understand, we won't get any more hints about, and we're stuck. Whereas if this is correct, if it really is all mathematical, that means very good news for physics. There is no roadblock. We still might not be creative enough to figure everything out, but at least we will know that there is nothing that we are in principle incapable of understanding. And our ultimate ability to figure things out better about our world will only be limited by our own imagination. We obviously don't know which of these two possibilities we're actually facing, but I think it's actually a pretty good working hypothesis to assume that it is possible for us to understand more and try our best, because you all know that there's no better recipe for failure in any enterprise than to assume just from the get-go that what you're trying to do is impossible, and therefore never really try your best. Now, if there's nothing fundamental preventing us from understanding things better and better and better, that means really that there is nothing in science that's totally off limits to a mathematical understanding. For example, consciousness. If consciousness can actually be understood as particles that are somehow moving in beautifully complex patterns that process information, then that would mean that I should be ultimately mathematically describable as well. And it was really interesting for me a few weeks ago when I was organizing a physics conference, because we had some neuroscientists who came, Giulio Tononi and Christoph Koch, and they have this fascinating idea now that they can understand why a rose has the fragrance of a rose and why the color red looks red in terms of mathematical shapes to do with the information processing that the particles in their brains do. And we don't, of course, know yet whether their ideas are going to turn out to be correct or not. But this is the sort of thing which it's going to be really fascinating to see how it plays out, to see how well they succeed. Because this hypothesis that it's all mathematical, it makes the firm prediction that there are no non-mathematical properties. So if any scientific endeavor can identify some aspect of nature and show that this cannot be described by math, that kills off the whole idea and rules it out. Now, we've talked about what this all means for the future of science, the future of physics. But I want to end today's discussions by talking about what it means also for us humans and for the future of our life here in the cosmos. We are in a place where it's very appropriate to talk about this because of its very venerable history. And when we look at our path ahead here, the fact that we've discovered that our cosmos is so much grander than we thought, some people take that to be depressing because they say, oh, it means that I'm much smaller relative to everything than I thought, and that hurts my ego or whatever. To me, it's actually the opposite. To me, this is a very positive thing. To me, the fact that we live in a much grander cosmos is actually wonderful. It means we have much more potential than we thought. It's much better to be in a really big universe than to find that you're trapped on this puny little place that you can't get out of, right? We have 10 to the power 57 times more volume at our disposal for life to maybe one day spread into. We have not hundreds or thousands of years of future we can dream about, but billions and billions of years. So what's going to happen? Well, you've all seen a lot of books and movies that have speculated about what might happen. There are a lot of optimistic scenarios. Some dream about life one day spreading and making much of the cosmos come alive. Then there are others who have more dystopic visions of the future, because the same technologies that have enabled us to fly into space and cure a lot of diseases also, of course, giving us various creative ways we can annihilate ourselves completely. We could have an accidental nuclear war. We could build superhuman artificial intelligence, which some people think would be awesome, and other people have conjectured will actually destroy all of human life and everything we care about. And there are a lot more, significantly more realistic scenarios, than this kind of bad movies for how that could happen. And we have many other ways in which we could mess up our planet as well. So in the last part of the book, I take a broad view of all of the most commonly discussed threats to our survival as a civilization. And it's very interesting that if you organize them like this, by how far into the future they're most likely to pose a great risk to us, what you find is that all of the most urgent risks, the ones on the left side here, that could wipe us out the soonest, are threats that we cannot blame on Mother Nature, like asteroids or the sun boiling off the oceans or our universe collapsing or these sort of things, but rather things we can only blame ourselves for, human-created risks. Now, this is also encouraging in the sense that it means that if we can avoid wiping ourselves out by getting our act together, we have a vast amount of time to take on these various other risks. And if you ask me at the end, I can tell you about quite promising technical solutions that exist to pretty much all of these problems, including the sun getting too hot and enormous asteroids striking Earth, as long as we can get past this immediate crunch here. Now, I confessed to you that physics professors tend to have a lot of bad habits, and I already gave you a pop quiz. Another bad habit I have is I like to give grades unsolicited. So I decided to give humanity a grade for Risk Management 101, based on how we're doing so far. So I asked some friends what they thought was a fair grade, and B+ was a suggestion. The argument being that, yes, we humans have been pretty reckless many times, like the Cuban Missile Crisis was probably playing Russian roulette a little bit too carelessly, but we're still here. B+. But I decided to actually give us a D-. And I don't know what that would be translated into in the British grading system. Can someone help me out here? D- too? So it's, okay. And I'm still known as a pretty lenient grader at MIT, you should know. So why is this? Well, it's very hard to estimate the probability that we're going to wipe ourselves out in any given decade. Some people say it's very unlikely, maybe only 0.001% each decade. Other people think it's more likely, maybe 1 in 10. Martin Rees has written in his famous book that he thinks it's maybe about 1 in 10. These kind of numbers might be considered acceptable back in the old days when, when 100 years or 1,000 years seemed like a really long time and we had no clue how much time we really had on this planet. But in the cosmic perspective we have now, where we have this enormous opportunity in billions of years, this is just absolutely ridiculous to be taking these kind of risks. There's no way we're going to last 1 billion years if we're this careless. So D-. Now, if you ever give somebody a low grade, they will come and complain immediately and ask you to justify it, of course. So I thought I need to justify this a little bit better. And I'm going to justify it with this very, very simple comparison between these two gentlemen here. Which one of these two guys is more famous? The usual answer I get is, who is Vasily Arkhipov? And there are clearly a lot more people have heard of Justin Bieber, even though today would actually have been Vasily Arkhipov's birthday had he been alive, so it's very appropriate. That's why I'm showing him today. Now, but we should ask a second question too. Which one of these two people should we really thank for us all being alive here tonight? Because he single-handedly stopped a Soviet nuclear attack during the Cuban Missile Crisis. I'll give you a hint. He's not Canadian, okay? and this reflects some pretty seriously screwed up priorities, I feel, for us humans. That something so important is nonetheless deemed to be just so irrelevant that we don't even bother teaching about it in schools or making nearly as big deal about it as Justin Bieber. So why is this? Why are we so short-sighted? We humans have figured out so much cool stuff about our universe. We have so much opportunity, yet we spend very little resources on actually safeguarding our future and trying to be good stewards for our planet. Why is this? Well, the most common answer I get when I ask people is, we just don't have the money. The economy is tough, and if we had more money, we would, yeah, sure, but can't afford it. But I'm kind of a numbers guy, so let's look at some numbers. There are some organizations I talk about in the book, in England and the US, etc., who try to raise money and do what they can to reduce these kind of risks. The Future of Humanity Institute here in Oxford is one such organization. The Cambridge Center for Existential Risk is another such organization. The Royal Institution, the Royal Society also put some efforts into these things. The best funded one is probably the Union of Concerned Scientists in Boston, in the US, in Cambridge. They get about $20 million a year that they raise, which sounds like a lot of money. But let's shrink that down so $20 million represents these few pixels here, and look at a few other things that Americans spent money on last year. It's really important things like plastic surgery. That was $10 billion per year. Or maybe air conditioning, and that's just air conditioning for US troops only, $20 billion last year. What about, oh, this is really important, smoking, $100 billion last year. Don't get me wrong, I'm all for personal choice. If one of you guys wants to light up, fine by me. But does this really reflect the relative importance of these two activities, the relative sizes of these things? I don't know. And I couldn't even fit on my slide here the biggest budget item for the US last year, because it's too large. So I have to actually shrink everything down to fit the military spending. So clearly, lack of money is not the real reason. Why else could it be that we're so careless about all these future opportunities? Well, another answer I very often get, especially in the US, is that it would simply be irresponsible for us to spend resources on risks that have not been proven. I hear a lot of people, especially on a particular US news channel, say it's irresponsible to spend money combating global climate change when it hasn't been scientifically proven, okay? So if you think about that for a moment, the easiest way to see the logical flaw in that argument is just imagine that you are in a store shopping for a baby carriage for the baby of a really close friend of yours, okay? And this very slick salesman comes over and says, hey, I have this really, really nice, robust stroller here for only 49 pounds 99 pence, and it's been on the market for over 10 years. We haven't had any reported safety problems with it at all. I'm solid buy. But then, for only 39 pounds and 99 pence, I can sell you this one. I know there have been some media reports about it sometimes collapsing and crushing the baby and stuff, but they haven't really been substantiated. And honestly, nobody has ever been able to prove in court that any of the deaths of these babies were actually caused by, manufacturing flaws by the manufacturers. So wouldn't it be irresponsible for you? Wouldn't it be irresponsible to spend 20% more money on this risk which hasn't been proven? So which one are you going to buy? Well, if you feel that it's silly to say that it's irresponsible to spend money on risks that aren't proven, and if you feel that it's rather the other way around, that it's irresponsible to not spend money on risks unless we can prove that they're not dangerous, when the life of one child is at stake, surely you'd feel the same way if we're talking about the lives of all children. Not just all children on the planet now, but all future generations that could live during billions and billions of years, right? So, in summary, we've talked about how research in cosmology has made very clear that we have much, much greater potential for the future of life than we thought. But we also have much more power to really make a difference from our better understanding between some pretty happy outcomes and some significantly less happy outcomes. So in summary, what I would like you to take away from this is that even though we humans are small, we really have a great power to understand and improve the world around us. So let's make a difference. Thank you.
You talked about roadblocks, and I think there is a roadblock. And you also mentioned the redness of something red. And before that, you showed a table with charge and lepton number. The thing is, redness wasn't in that table.
That's right.
And I was just wondering how, do you think that we can derive redness and painfulness and the blueness of something from simply, doing mathematics on paper and combining these values like charge and mass? Do you think that you can ever derive the painfulness of something painful from that?
That's an absolutely wonderful question, an extremely hard one, which has become known in neuroscience as the hard problem of neuroscience. Why is it that something that from the outside looks like a bunch of quarks and electrons moving around can from the inside feel pain or love or any of the emotions or sensations that we're so familiar with? And the remarkable idea that I mentioned that Giulio Tononi and Christoph Koch are pursuing here is But they really believe that there is, that the answer to your question is yes, that there will ultimately be a way of looking at a room full of quarks and electrons and understanding why is it, understanding first of all whether there is any consciousness in there at all or not. You would think maybe naively that first of all you need to have these particles doing something a lot more complicated than just being stuck together in a rock. Right? They have to be in a computer even. They have to be moving around in a much more complex way so they can process information. Right? But that's clearly not enough to feel conscious. I would be very surprised if any of your laptops is conscious. But they have some ideas for what additional kind of things these particles have to be doing in order to feel subjectively conscious. Do I claim to know whether we can ultimately do that or not? No, absolutely not. I'm just saying, raising the possibility that either we can or we cannot. And I think the best way to pursue this further is to really continue these kinds of research and see what they get. What they do, for instance, is really fascinating. They'll take patients who are in the hospital to be screened for epileptic seizures, and they will measure all sorts of things about the properties of what their neurons are doing, and then they will ask them at the same time, are you aware of this, are you aware of that? And they find that there are a lot of processes they can see happening in the brain that the patient is not aware of, and others that they are aware of, and they even have a pretty detailed theory of what they think it is about the particle motions which corresponds to consciousness. I would recommend a book called Phi by Giulio Tononi, which I think you'll find very interesting. And all I'm saying is I think this question you're asking is very deep and very profound. And even though Christoph Koch is now a very established neuroscientist, he was warned to not research consciousness until after he had tenure because it was considered sort of too flaky for his neuroscience colleagues. I think, quite contrary-wise, the question you're asking is really, really interesting. And we should stop shying away from it, because one day, if you have a patient in the hospital and they're unresponsive, it would be really nice to be able to know if they're actually conscious or not, even if they can't exhibit any behavior, or whether an animal who some meat vendor claims can't feel pain, is actually conscious or not, or whether some future very advanced computer is actually conscious or not. And so I think it's research worth pursuing with an open mind.
We got the gentleman in the front here.
Hi. Thank you for an informative talk.
Thank you.
I was just wondering, you showed those numbers. There are numbers and constants and laws, but do you think that they're just local phenomena? I mean, if we look at the bigger picture, if we go far enough, maybe these constants will not remain constants, do you reckon? Or
that's a very deep question also. Another constant that's very striking about our world is 8, the number of planets in our solar system, with apologies to Pluto. And long ago, that would have seemed also like something that maybe should go on this list, when people only knew about one solar system. Why are there 8 planets in it, in our universe? Now, of course, you just laugh. That sounds like an absolutely dumb question. Because, of course, we know there are other solar systems with 7 planets and 3 planets, and that number 8 isn't telling us anything fundamental about our cosmos. It's telling us part of our address in the cosmos. You could tell the intergalactic mailman, go to that galaxy that's shaped like this, that solar system there with 8 planets. And she'll be like, oh yeah, I know where you live. And could it be the same for some of these other numbers? For a long time, there was this dream that you could calculate them all from first principles. You take pi and you take the square root and do something clever. But more recently, we begin to get a sinking feeling that many of these might be no more fundamental than the number 8. Just as, water, if you look at the equations for water, you find that it has 3 different solutions: liquid, gas, and solid. String theory has suggested that the equations for space have more than one solution, maybe even 10 to the power 500 or so. So maybe our space itself can freeze or melt, etc. And moreover, the theory of inflation, which is the most popular theory we have for what put the bang into our Big Bang, has this funny property that when it stretches space out and makes more space, it'll actually make space of all the different kinds. And in different kinds of space, many of these numbers would be different. And if that's true, when we measure these numbers, we're actually then not learning as you're intimating, anything fundamental about nature, but we're again learning more about our address. You would say, oh, we're in the part of space where this constant is so-and-so. And it's not just that this idea is physically motivated, because we now have a mechanism for how it might get this way. But there's also a funny hint of it in that Steven Weinberg, famous Nobel laureate, wrote a paper many years ago before we had the mechanism, saying that if it's like you say, that there's a different amount of dark energy in different parts of space, that being the very last number on the list here, which you might not hear, the crazy one, which is about 10 to the power minus 123. He realized that if you have too much of that, it just poisons galaxy formation. You have to have a very tiny amount to get any galaxies, so that would create a big space, which is kind of like the Sahara Desert, with only the occasional oasis, where there are galaxies. That's a prediction he made, and he said, of course, if we're looking from a random galaxy, then that means we're going to find a very small value of this number. Most people dismiss this until dark energy was suddenly discovered in the sky, the accelerating universe discovery, which just got the Nobel Prize. And we're in this funny situation where the only scientific explanation for why this number happens to be in the very, very narrow range of values which allow galaxies happens to be exactly what we have. So this so-called level 2 multiverse idea that there's just a big space which is more diverse than the part of space that we can see has gained a lot in popularity. Doesn't mean it's true, of course, but it's a perfectly valid scientific theory because it's predicted by inflation and so forth. And it's a very interesting open question, then what about all the other numbers? No, go for it.
There's a microphone coming.
Have you personally come to believe that everything is mathematically predetermined and there is no such thing as free will?
I'm all for personal questions. I try to avoid believing anything. That's not my job as a scientist, to believe certain things. I try to be very open-minded. So I'm more of a betting man. I'm happy to give you odds on various things. Your particular question here was whether I think everything is mathematically predetermined. Was that it? Or and that we don't have free will in some meaningful sense?
Yes, I mean, if the universe is sort of determined by a series of equations, then you could forecast exactly what is going to happen.
So the free will, you're asking all the awesome philosophical problems. We've got the hard problem of consciousness, now we've got free will here. Everybody seems to have a slightly different meaning of what they mean by free will, which of course skews what the answer is going to be. Seth Lloyd, at our recent physics conference I mentioned, gave a very nice, crisp definition. He said that operationally free will means that you cannot predict what you're going to do a minute from now in less than a minute. The most efficient way to predict it is just to go through the whole 1-minute thought process between now and then. There is no sort of shortcut, right? And in that sense, you can actually prove, using some deep results in computer science, that even just a classical computer doing some very generic hard calculation has free will, in the sense that it can never figure out what it's going to, what conclusion it will reach without actually going through all the steps. So if you're trying to decide, should I propose to this person I love or not, you have the feeling in advance that you don't know, or maybe you kind of do know in this case, but what you're going to ask. You still feel you have to go through all the thoughts, and that's not an illusion. It's real. Now, in the actual world that we're in, we know it's even more complicated than that. So you have even more hope for more other definitions broad definitions of free will, in the sense that, first of all, we're not in Einstein's classical universe where time is just the fourth dimension and past, present, and future. There's only one future. Quantum mechanics suggests that if anything, the future is more like a branching tree where there are many different ways it could go. So I wouldn't lose any sleep about not having free will. I would continue feeling good about your mind, knowing that the thought process you go through is actually exactly what it is. It's making a meaningful difference. You also asked about my odds about things really being mathematical. And I mean, I would put pretty good odds on it. Definitely, maybe 90% or so. Would I bet my firstborn son on it? No. But would I bet enough to write a book about it? Yeah.
So we've got one up there. So if we go to the gentleman in the balcony.
You mentioned your MIT colleague Seth Lloyd, who also claims the universe is mathematical, though a particular type of mathematics, that the universe is something that computes. And as we know from Turing, that's a form of mathematics as well. So any comments on whether this mathematical universe is something that computes? And second, the example you just gave of his reply on free will also illustrates that mathematics shows limits to knowledge. NP-complete problems, Gödel's theorem, things like that.
Absolutely.
So earlier in the slide you said mathematics gives us unlimited possibilities of knowledge of the universe, but does it also tell us where the roadblocks are in our knowledge?
Great. So you raised two separate interesting points. Let me comment on them in turn. First of all, Seth Lloyd's idea that our universe is a computation, or more specifically a quantum computation, would be simply one of the different parts of the level 4 multiverse, one that actually has the mathematical structure of quantum mechanics in it. And then there will also be others. If there is a level 4 multiverse with parts described by all possible mathematical structures, then that's probably also like the Sahara Desert on steroids, where the vast majority has nothing like life in it. I mean, the vast majority of mathematical structures don't even have any kind of space or time in them. Only very few, like Minkowski space and so on, and do, right? So Seth's suggestion is basically a special case of mine. And then for your very interesting question about Gödel's incompleteness theorem, so just to bring everybody in on this, Kurt Gödel threw a huge monkey wrench into Hilbert's vision that we should be able to prove that mathematics is consistent by showing that in any sufficiently powerful mathematical system, there are some statements where you can neither prove them or prove them. And this would seem pretty embarrassing if there are some properties of nature which are in some sense undefined, since nature seems to kind of know what it's doing, right? And so one very radical possibility that I explore in the book here is the question and assumption that very few physicists actually question, which is the assumption that there is something truly infinite in the physical world. I love infinity in mathematics. I fell in love with Cantor's hierarchy of infinities at an early age, etc. But we have to remember that all of the Gödel problems come from infinity, always. And if we look at the physical world and I ask, how long is this laser pointer in centimeters? 11.34875. I would have to give an infinite amount of information to answer that question, if this space is a true continuum with infinitely many points. Yet we've never measured any number in all of physics ever to more than 17 decimal places. And we have very good reason to believe that it doesn't even make sense to talk about distances shorter than 10 to the minus 34 meters, the Planck length. So I think we have to have an open mind about this. That I get even more worried about this when I teach physics courses at MIT, because they're always infested with infinity, left, right, and center in everything I do. If I teach a course, can you hear me, for example? Raise your hands if you can. That's because there are sound waves going through this room, right? If I'm doing some courses on waves at MIT, I start by saying, let's assume there are infinitely many, that air is continuous. And at each of infinitely many points, you can define a pressure and a density. Then you can write down this wave equation and do a bunch of fun calculus and solve it. It's beautiful, easy, and it gives you all of acoustics. But is it true? And we know it's patently false, because this air is made of atoms. It doesn't make sense to talk about the pressure of one atom if you look on really small scales. So this was just a useful approximation, which we now know to be just really useful when you're looking at sound waves that are much longer than the spacing between the atoms. It just turns out it's much easier to assume that there are infinitely many infinitesimal atoms than to have to keep track of where 10 to the 26 atoms are, right? So I'm just raising this as a cautionary tale, because we can't be so arrogant that we take for granted that the other continuum assumptions we make about space and time and so on aren't also just excellent approximations. I don't think we honestly know one way or the other. And moreover, many of the most embarrassing problems we face in cosmology now that I talk about in the book come from the assumption that space is continuous and can be stretched ad infinitum. So most importantly, I said that my job as a physicist isn't to believe things. I think rather my job as a scientist is to to have such an open mind, an open enough mind that I try to question every single assumption, and infinity is definitely on my suspect list.
In corporate life, more and more, they talk about evidence-based leadership. And basically, there are more and more numbers out there, more and more data, so you don't take any decision unless you have thousands of numbers and examples to back it up. And yet, some of the right decisions in both corporate life or in war have been taken totally against the numbers.
There's also a famous quote, of course, that there are three kinds of lies. Lies, damn lies, and statistics. So I think it's all about what we ultimately do with the numbers and the extent to which we're willing to actually listen to the evidence as opposed to just manipulate it to suit our own means.
I know you said you didn't have beliefs. I just was wondering what odds you would therefore put on mathematical realism, because you seem to be going in two different directions. In one sense, the universe is mathematics. Maths is at the base, and yet the maths that I'm aware of are ideas in my head. And are they therefore just invented? They seem to be created, because if you're taking a physicalist line and saying that there is nothing, that mind is ultimately reducible to matter, which is reducible to maths, my ideas of maths are reducible to maths.
Yeah, we got right back to your bar. Exactly, we got right back to the bar brawl that you described, right? People ended up shouting at each other about whether mathematics was invented or discovered. And this is a wonderful question, very deep question, which indeed, as you have first-hand evidence of, even mathematicians argue about, right? I think it's very important when we talk about, first of all, whether mathematics is invented or discovered, to distinguish between the language of mathematics and the structure of mathematics. So take Plato, for example. He was really interested in how many different perfectly regular so-called Platonic solids there are. And he felt that he realized that there were actually 5 of them. The tetrahedron, the cube, the octahedron, the dodecahedron, and the icosahedron. Now, he invented the name dodecahedron. He could have chosen to call it the schmodecahedron or whatever that would be in Greek, you know. But he didn't invent the fact that there were 5 of them. He couldn't just invent a 6th Platonic solid, because it really doesn't exist. So that's the structure of mathematics, the part that he felt he discovered. Whereas most of what we see written in math books is just notation, the language we use for describing these various structures. I have a colleague at MIT, Professor David Vaughan, who has a poster on his wall of the Lie group E8, which he spent a decade of his life dedicated to exploring. He would be really pissed at me if I suggested that he had just invented that and made it up. He feels it's out there, just like the dodecahedron, and he is uncovering its properties in the same way that I feel that we humans have discovered the planet Neptune rather than invented it. And there's this interesting similarity. We feel that we discover Neptune and the other things in the physical world rather than invent them, and mathematicians feel they discover those structures. In both cases, we invent language to refer to them. The name Neptune, we could have called it Neptune or whatever. Right? And then we invent the language, the symbols we use to write numbers, but the structures are sort of out there. So the mathematical universe hypothesis says that these two kinds of structures, the mathematical ones that are out there and the physical ones that are out there, are ultimately one and the same. And if you look at it at any sort of advanced physics description of the world, you'll see that people talk about space-time and general relativity being a 3+1 pseudo-Riemannian manifold. Then you can go to a math book and see people talk about 3+1 dimensional pseudo-Riemannian manifolds as math structures, or Calabi-Yau manifolds, or Hilbert spaces, or whatnot. So that's the correspondence that I'm speculating might actually hold, not the language that we are simply inventing.
Do we have anyone up in the gentleman with the hat?
Yes, you mentioned a little while ago about Gödel and about the fact that it's all based on infinity, or it starts to all look peculiar when you bring that in. And you also mentioned about the Planck length and so on. I was wondering, do you have any views on whether you think that space might turn out to be quantized rather than continuous?
My personal guess is that indeed space is quantized at some level, and that this continuous space, which we were just talking about 30 seconds ago, the Riemannian manifold and so on, is again just going to turn out to be a very convenient approximation, which is not exactly the truth. Even John Wheeler already many years ago speculated that if you zoomed in enough at space on really tiny scales, it would be some kind of weird quantum foam, and only when you zoom out and don't notice all that small scale peculiarity, only then does it look like this smooth, continuous space that we are very familiar with.
Thank you.
So just to test our microphone bearers, the gentleman right in the middle at the back there.
When you showed us a map of the observed universe, you'd expect it to be some kind of sphere about the size of however many light years we've observed, up to the point the galaxies rather than the background radiation, when it was basically, I'm asking about the shape. It's this kind of hourglass shape there. I was wondering if there's a particular reason why it's that shape rather than some kind of sphere.
Thank you for asking and quite straightforward question. So the reason for this, that we have galaxies mapped in this hourglass shape, is simply because we haven't been able to look so well in these directions, because our own galaxy that we live in is kind of blocking our view over there and there. So this is the Sloan Digital Sky Survey, the most ambitious 3D galaxy mapping project so far, which I had the fortune to get to work on with my colleagues. So we have this big telescope which can measure the distance to 640 galaxies per hour automatically. But once you start looking in directions, when you're looking into the Milky Way, there's so much dust between the stars that it sadly blocks out a lot from view. So this is not telling us anything fundamental about our universe, but just about our human incompetence of choosing to live in a galaxy.
Any similarly straightforward questions, or failing that? In fact, this gentleman here has had his hand up for quite a long time, in the front row.
If you could go back to your chart of the parameters, one of the things about the language of mathematics is that it can express very neatly huge differences of scale, but surely it's not the language that you can possibly, reality may be mathematical, but its properties at other scales need other language. You are one person. You can't possibly have the property of being a lecturer without there being some other people. So it depends on what scale. The property of being a lecturer only applies to a world that is, in the scale of more than one person. And indeed, the idea of one person is rather difficult conceptually.
So I'm not 100% sure that I understood what you meant, but the way I understood what you said, I agree with it.
So it was a straightforward question. Excellent. So any more up in the gallery? We've got was one round the side there.
You spoke about the risks that we face in the future, the existential risks, things that might destroy us. I was just wondering if you could say to young people who want to do something about these things, what would you say they should do?
Well, first and foremost, I would again like to encourage people to not feel powerless. It's so easy to feel powerless in this day and age. And I have to confess, you said if it was okay to ask personal questions, I'll make a personal confession. For much of my career, the more I learned about the vastness of the cosmos, the more insignificant I started to feel. Until suddenly I made a total U-turn, and part of the reason for that, which I'm happy to share, was I'd sort of always taken for granted that there must be a lot of aliens out there that would bail us out in case we screwed up here, because there's just so many stars out there, there's got to be life somewhere, right? But if you actually do the numbers, which I do in the last chapter here, in this finite volume that we call our universe, the evidence that there's all these aliens out there is actually on pretty shaky ground scientifically. We have loads of planets, we know that, but we have very little idea of what the probability is that the life will evolve on any given planet, all the way up to the point of building telescopes and doing the sort of things we do. Even if it turns out it's pretty easy to get up to the level of dinosaurs, our dinosaurs didn't seem to be too keen to start building telescopes. They stomped around for over 100,000 years without even forming a royal institution, right? 100 million years, sorry. 100 million years. So if we consider for a moment the possibility that we are actually the only civilization with telescopes in our universe, then we shouldn't feel insignificant at all. Now, if you feel that those galaxies out there that we looked at were beautiful, why are they beautiful? Because of your consciousness that perceived them, right? If we wiped ourselves out and weren't here, they would just be a giant waste of space, as far as I'm concerned. And in that sense, we shouldn't look for our universe to give meaning to us, but rather it's us giving meaning to our universe. Those galaxies only became beautiful and meaningful about 400 years ago, when Galileo first pointed a telescope to the sky, to the heavens, right? And moreover, if this is the only civilization in our universe that's this advanced, then if one day much of our universe has come alive, that means it started here. I also said how I think we're kind of at a fork in the road right now, which this illustrates. I don't think we can just muddle along like this, taking all these risks for many generations without either getting our act together or wiping out. So I think the difference between a really inspiring future and a dead one for our universe is going to be made quite likely actually in the lifetime of us. And so if one day our universe is teeming with life, I don't know how our descendants are going to think about us, but I'm confident that they're not going to feel that we were insignificant, because we made all the difference. So the first thing I would say to young kids here and to all of you is, don't feel insignificant, because you're certainly not. What you do here on this planet in your lifetime could actually determine the fate of all life in the future of our cosmos. How much more significance do you want, guys? Come on. And second, if you want to do something more concrete, now that you feel more empowered, get in touch with some of the organizations who are actually thinking really hard about this. You're fortunate because here in England, again, the Future of Humanities Institute and the Centre for Existential Risk in Cambridge, there are also some wonderful effective altruism organizations based in Oxford and London who are putting real creative thought into how a small number of people can really make a difference for the better. And so go out, Google them, and I bet you can find good ways of putting your creativity and idealism to work.
Okay, we've got this gentleman's been waiting quite a while.
It doesn't follow, because mathematics has an objective structure and physics has an objective structure, that physics is mathematics.
Absolutely correct.
So surely the possibility, the likelihood is that mathematics represents the set of possibilities for physics rather than the actuality of physics. Otherwise, why would we need evidence? Why can't you just dream the stuff up and everything that you say is true?
So you make two separate interesting points there. The first one about the difference between actuality and potentiality, in other words, the distinction between our universe having only mathematical properties versus the possibility that all different mathematical structures also exist in some sort of real sense. That distinction I talk a lot about in the book, and I make an argument for why that is so. I won't bore you with it here. But for the second question, why can't we just dream, in that case, dream stuff up? Because if everything mathematical can correspond to a real world, surely you can dream up whatever math you want. There, I actually disagree. It's remarkably difficult to come up with mathematical structures that are actually self-consistent and hang together. So we talked about Plato, for example, with his Platonic solids, right? There were 5 of them. He couldn't just dream up a 6th one. It just wouldn't exist.
The point is that there is a large set, set of possible mathematical structures.
Yeah.
And there is a subset of that large set, the set of physical structures. And you can't simply say that every mathematical structure must be a physical structure. Otherwise, you wouldn't need to have CERN. You wouldn't need to have physical evidence. At the moment, our convention is that we say, you haven't proved anything in physics unless you've got evidence for it. You can make a mathematical model, that's fine. But until you have evidence that it is actually true, it isn't physics. That's the distinction I'm making.
Okay, so first of all, I hope I convinced you that I'm all for evidence. That's why I've spent so much of my career gathering terabytes of data and ruling out a lot of cosmological models. To me, the distinction between physics and speculation is precisely when you have evidence and you can rule out models. Notwithstanding, if it is in fact the case that every mathematical structure corresponds to a physically existing one, which may be wrong or it may be correct, that there's two logically possible hypotheses, right? And again, I'm not into saying, I don't think my job is to believe in a hypothesis. I'm interested in exploring them. If it were that way, then we should still build CERN. We should still keep doing all our physics experiments. We would just motivate them in a slightly different way. And just as it was interesting to find out that there are 8 planets by building expensive telescopes, right? Even though we know that there are other solar systems with other number of planets, we wouldn't say anymore that the 8th we discovered tells us something fundamental and unique about reality, but rather we would say this tells us something about where we are in this universe and what kind of solar system we're in, which is still super interesting, as interesting as before. And likewise, if there is one universe where string theory is correct, which is described by string theory, and there's another one where it's described by loop quantum gravity instead, and string theory is wrong, then by studying these things and building CERN and so on, we would then be finding out which one of the two we're in. Just like we found out that we're in the kind of solar system with 8 planets instead of the kind with 6. So I think it doesn't change anything much in the motivation to do experiments in the day-to-day. It just gives you a different perspective of what we're doing, and that we're learning not fundamental things about the ultimate reality, but that we're learning more and more about our place in it.
We have 5 minutes left. I'd like to really quickly take up hopefully just one of those with my own question. You mentioned that space, for instance, we look at space and it's only got mathematical properties. And I was wondering sort of what a non-mathematical, what you'd find and say this is a non-mathematical property of this object, and so we've sort of failed, we've hit one of our roadblocks.
That's a wonderful question. So let's rewind a little bit and pretend that that's the year 1500 or so. Or let's actually go a little forward again. So let's bring Isaac Newton in on this conversation, and ask him that question. So to him, clearly the motions of planets and the motions of objects under gravity was mathematical, because he'd figured out for the first time how to describe all that. But to him, many of the properties of magnetism and so on, would still have seemed very mysterious and not at all obvious that you could do with math, because Maxwell's equations came only in the 1800s. So then suddenly, something which seemed kind of non-mathematical, light and all this stuff, yielded also to mathematics. But even then, I think James Clerk Maxwell would probably have been pretty stumped if you asked him to explain why is it that wood feels hard and your hand feels soft. Is that mathematical, something that you can describe with math? I think Maxwell would have been really stumped by that and said, I have no idea how to do that. Yet, what happened? We got the Schrödinger equation of quantum mechanics, which beautifully describes the whole subatomic world and lets us actually calculate all these properties of softness and hardness and colors and all these other aspects of matter. So ultimately, the only way to know whether something can be described mathematically is to try really hard, I guess, and see if you ultimately fail. And it's quite striking how many things which seemed very unmathematical actually backed off. And that's why I'm encouraging people to keep thinking about the things which today seem so non-mathematical, like what you so beautifully asked about there, the hard problem of consciousness, for instance, and see if it's going to go the same way as the softness of my hand and the hardness of the table.
Thank you very much. So time for a couple more, just quickly. So with this gentleman here?
Just taking you back to the answer to your last question there. Does that equate to saying that it's impossible to disprove that everything is mathematical? So saying that the only way to find out if it is mathematical is to try really hard to prove it.
No, it's, you know, we should never say never. We can never be so sure what clever things other people will come up with, right? It's perfectly plausible that someone here in this room even will come up with some really clever proof that, look, here's a physical phenomenon that can't be described mathematically. And if that happens, it would be falsified, right? Whereas conversely, if you can prove that it's impossible, then you've proven me right, haven't you?
So we've got time for one last question at the top, and then I'm afraid if anyone else has questions, they can buy a book later off him, and I'm sure.
Hi. They say that black holes break maths. Do you think that they're just doing the wrong maths? And from that, if the universe can be described by maths, then what about the kind of maths that can't be defined, like, or can't be proven, like 1 divided by 0 or something?
Okay, so two separate questions there: black holes and then undefined mathematics and so on. So the business about 1 divided by 0 doesn't bother mathematicians nearly as much as the Gödel issues, of course, because it's the way you normally would define the real numbers. You define it in such a way that that's not a problem, even though the calculators we have let us punch in things wrong. But coming to black holes, this is clearly one of the great frontiers of our ignorance right now. And we've seen it again and again that to make further progress in physics, it's often very helpful to focus in on exactly the things where we're embarrassingly ignorant about what happens. First of all, when black holes were first found as a solution to Einstein's equations by Schwarzschild, you know, they seemed so weird that even Einstein was kind of skeptical about them. And it wasn't until the 1960s that we started to take seriously that maybe they even exist, these weird things. Now we've gotten kind of jaded and so used to that we don't give them names anymore, but just numbers, the black holes in the sky. But we have other problems with them now. First of all, as you know, when we formally solve Einstein's equations, you have the singularity inside, where truly infinite things happen, and worse than that, where you can't predict with the laws of physics what's supposed to happen next. And even more embarrassing, if you take the traditional Big Bang theory and go backward, you also realize that everything here came out of a singularity, and you're not supposed to be able to predict what came out. So like, everything that happened was sort of random. This is why the theory of inflation was invented, partly to get rid of this. But the black hole thing, the plot just keeps thickening. As you've probably followed more recently, it now seems pretty clear that what happens inside of black holes, at least the real astrophysical ones, which are spinning a little bit, is not at all what the Kerr solution for black holes says, because there's weird instability that forms at the inner horizon as opposed to the event horizon, where things go very unstable and we don't really know what takes place. And then most recently, you probably saw Stephen Hawking just a few days ago with a new paper talking about what's known as the firewall paradox. If black holes evaporate, how can the information get out? We had a big discussion about this at this physics conference that I was co-organizing a few weeks ago, and I think all you need, it kind of says it all, that this was the most acrimonious panel debate we had at the whole meeting, and everybody was totally up in arms, and you know, the world's leading black hole experts really don't know what to make about this. All I would say is, I think it's pretty clear that if you want to really unify gravity and quantum mechanics, understanding what's really going on with black holes is going to be a master key to unlocking this puzzle.
Okay, well, thank you very much.
Thank you.
Cheers.
Now we'll close now looking at the history and future of the solar system, and I'll point out a couple of things that if I go forward one screen, you'll see something that looks like this. So you'll notice on The left-hand side, the planets that exist at that time, including even, for example, down the bottom there, a fifth giant planet in the solar system, and shows the ordering out from the Sun. Then you see the orbits of the planets on the next diagrams in the middle. You notice these numbers down the bottom here shows the age of the Sun since fusion has kicked off. So currently showing on this slide here, it says the Sun is 5.4 million years old, down the bottom left. And the time above it is the number of million years different from today. Then up on the top right-hand side, you'll see the Hertzsprung-Russell diagram, and the little X there shows where the Sun is going along that diagram, and the properties of it at the time. So what the temperature is, and its luminosity, radius, and mass. And you'll notice that things, number one, that the planets, some of the planets exist before the Sun actually heats up enough through gravitational contraction to turn up. To turn on fusion, and when it does turn on, things move very, very quickly. And in fact, to see some of the detail that's shown in this video, which only goes for about 3 minutes, you'll have to stop it at certain frames to look at the explanations they give. It moves quickly. And with the death of the universe, I'll now close the meeting, and we'll see you next month, hopefully.